Hello, I would like to perform a calculation of a resistor that is a cylindrical resistor using the ideal cylindrical resistor equation, and then from there calculate electric current through that object and also the electric field that is induced in that object. So let's look at this calculation. What is the resistance of a 2.54 centimeter diameter rod of pure tungsten that is 20.0 centimeters long? Now, tungsten's a pretty good conductor, and when it's made very, very, very thin, it has sometimes been used for things like incandescent light bulb filaments. But this particular piece of tungsten is going to have a small resistance, I think, because tungsten's a pretty good conductor. Now, by the way, we know the equation for resistance of a cylinder. In fact, let me go ahead and bring up a cylinder here on its side. So the idea is that this cylinder has a certain cross-sectional area A. It's made of a certain material, rho sub r. And then in this case, that's tungsten. So I'm just going to do tung for tungsten. And then also we know that it has a certain length. So the equation that relates those parameters together is the resistance of a cylindrical conductor is going to equal to the resistivity. That's this rho r. This is not mass density. This is resistivity of the tungsten in this case, times the length of the wire divided by the cross-sectional area of the wire. Okay, well, we know what the length is already. The cross-sectional area is probably going to be given by the cross-section of a circle. Okay, so that's what we should be looking at in terms of the geometry. So A should equal to pi r squared. So pi times the radius squared. Let's get these other parameters. The length here is 20 centimeters. So that's 0.200 meters in SI units. Now the diameter is also known to be 2.54 centimeters. That's 0.0254 meters. So the radius is exactly half of that diameter, which is 0.0127 meters. Okay, so let's see if we can calculate this resistance. So this resistance should be the resistivity of tungsten, which, by the way, we should look up. Now, this is known in a lot of physics books, engineering books, so on and so forth. The resistivity of tungsten is about 5.6 times 10 to the minus 8th, and that's units of ohms times meters. So let's move this calculation of R down here then. Okay, so let's now put the numbers into this calculation. So this is 5.6 times 10 to the minus 8th, ohms times meters, that's the resistivity of tungsten, times the length of this resistor. Okay, so that's going to be 0.200 meters, and then the cross-sectional area is going to be pi r squared, r being 0.0127 meters, and we have to square that. Okay, so let's go ahead and get this value. Okay, so let's go to the calculator. Okay, so let's go ahead and get this value. And let's clear for now. So alpha F1, let's do the stack. Okay, and let's perform 5.6 times 10 to the minus 8th, 5.6 times 10 to the minus 8th, times 0.200. By the way, when you do the calculations, you can just do 0.2 or 0.2. It'll give you the exact same value. Significant digits aren't really counted in the calculator themselves. And then we need to divide by pi, so second pi key, times an r squared. So that's 0.0127, and then the x squared button. Enter. Okay, so let's write this down. Okay, it's about 2.21 times 10 to the minus fifth. Okay, so this is 2.21 times 10 to the minus fifth. And that's going to be units of ohms, because that's the SI unit of resistance. Okay. Put a box around this. Always a good idea when you have answers to be clear about what the answer is. Okay, looks good. B, what current flows when 10,000 volts is applied across this rod? Well, I think we should use Ohm's law. As long as we assume this is an ohmic device, that the current is linearly proportional to the voltage, then we should be able to use Ohm's law. So I think that delta V, that's the voltage difference, over R should equal I, which is the current. And in this case, delta V is exactly 10,000 volts. So let's just put those numbers in. 10,000 volts divided by the resistance we just found, 2.21 times 10 to the minus fifth ohms. Okay, so let's get that value. Okay, so back to the calculator. So we have 10,000. Oops, let me stack this up. Okay, better. 10,000 volts divided by 2.21 times 10 to the minus 5, and that's ohms. So that's a pretty large number. I'd rather have that in scientific notation. So I'll go mode, I'll go to scientific notation, hit enter. I'll second quit. I'll go back to here and recalculate this in scientific notation. Okay, looks a little easier to write down. So it's about 4.53 times 10 to the 8th. So 4.53 times 10 to the 8th, and that's going to be units of amperes. Alright, that's an extremely large current. This is a very, very small resistance. What is the corresponding electric field? Now notice I wrote this equation down because this is an equation that I think is often missed and is often neglected, but it's useful to know that J, okay, so this J is the current density. So that's going to be units of electric current divided by cross-sectional area. Well, and then sigma C is the conductivity, in this case, of the tungsten. Now the conductivity is the same thing as the reciprocal of the resistivity. And because I looked that up, that turns out to be approximately 1.8 times 10 to the 7th. And that's going to be units of 1 over ohm meters, because it's just the reciprocal unit of the resistivity. By the way, resistivity and conductivity are a property of the material. Resistance is dependent upon the geometry in an actual device. So I think that since this is I over A, and we want to get the electric field, we need to divide by the conductivity. So we can say I over A sigma C of the tungsten, that's that's not surface charge density, that's conductivity, is equal to electric field. So let's put the numbers in. By the way, this is the magnitude of electric field. We know electric field's a vector. It should point in the direction of the conventional current. But let's put those numbers in. Okay. So, let's see. The current, I believe, is that 4.53 times 10 to the 8th amperes. Okay. And then we're going to divide that by the cross-sectional area. That's the pi times r squared. That's 0.0127 meters squared times the conductivity constant of tungsten. 1.8 times 10 to the 7th 1 over ohm meters. All right. So let's get this value. So over to the calculator. So let's stack this up. And let's do 4.53 times 10 to the 8th. And let's divide that by pi, there it goes, times 0.0127 times 10 to the, or sorry, that should just be 0.127. Sorry for that. And then squared. That needs to be squared. And times 1.87 times 10 to the 7th. Okay, so I think this is what we need. Okay, so let's write this down. 4.78 times 10 to the 4th. Okay, so this is 4.78 times 10 to the 4th, and that's volts per meter. Now, by the way, we could also express this in newtons per coulomb. That's the exact same unit for electric field magnitude. All right, I think that ends this problem. Thank you very much for your attention, everyone. Please smash that like button if you enjoy this video and content, and please subscribe to the channel to grow the channel. And also, please share this content with those in your sphere of influence. Thank you for your attention, and I will see you in the next video.